Hi guys, in this video we're going to talk about the next application of dot and cross product, which is the volume of parallelepiped and tetrahedron. Okay, parallelepiped is actually consists of 6 faces of the area of parallelogram. Alright, 6 faces of the area of parallelogram to create this object, right? And the volume will be calculated based on that. Okay, so it has 6 faces, right? 6 faces, just like square. And to calculate the volume of parallelepiped, right, we are going to multiply the area of its base, which is, it can be this one or other faces, because they are the same. Right, we're going to multiply the area with the height. The height should be perpendicular, right? Perpendicular distance between the base with the opposite face. So if this is the base, it should be perpendicular to this one, right? In order for us to calculate for the volume, first we need to define 3 vectors A, B, C, as you can see here, and these 3 vectors will represent the edges, right? By the way, all of this line here is known as edges, and all of the side here is known as vertex, right? So for this one, we are going to use 3 vectors to represent the edges, and this, as you can see, the 3 vectors or the 3 edges connected to one vertex. Right, so that is actually the idea, right? The component that we're going to use in calculating the volume of parallelepiped, right? So we define 3 vectors A, B, and C, and of course, because it is 3-dimensional, we have 3 components X, Y, and Z here, right? The volume is equal to the magnitude of their scalar triple product. So we're going to multiply it, right? So this is the magnitude, and this is the formula inside, where you see we have product, cross product, right? And then also dot product. Okay, so if you can see here, we have a cross product in the bracket, and this is how we actually calculate cross product before, right? And this is a let me change. Alright, so as you can see, this is how we calculate cross product before, where we arrange it in a form of a 3x3 matrix, where you have I, J, K, the component of I, J, K at the first row, and then the component of the first vector B, second row, and then the component of C at the third row, and then we'll calculate it as we calculate the cofactor method, right? And at the end, we are going to have a new vector that consists of I, J, and K. That is cross product. And then if you can look here, we multiply it with vector A, which also another vector, which also have the component of I, J, K, but the difference is that we are not conducting cross product, we are conducting dot product. So basically, we just multiply each of this component of A into each of the component of as a result of B cross product C. In other words, what does it actually happen is this. Right, as you can see, all of the component of A being input at the first row right, as a substitution of I, j, k, because later when we conduct a cross product, at the end we need to multiply I with the difference of this, j with the difference of this, and k with the difference of this, right? So still, as for this one, that is what actually happened. We had to multiply a with this operation, and a2 with this operation, and a3 with this operation. Hence, they are the same thing. So after we obtain the vector, right, the new vector, right, next is to find the magnitude. Okay, so that will be the volume. And by the way, when you see this is not actually the dot product. This is just the scalar multiplication. Right, we're just going to multiply each component, right, with the operation of cofactor. Right, you're going to see more of this on example after this. Right, now after we have calculated this, we can later find out the magnitude, and that magnitude will become the volume, as I said before. Right, now there's one property that you might want to know. If this calculation equal to 0, meaning there is no volume. So when there is no volume, meaning that it is not a parallel pipe. It is just a one flat plane, just a plane with no volume. That's why it is 0. Okay, and next we have tetrahedron, which is this shapes like a pyramid. Here is a tetrahedron. Difference is that it don't have 4 edges on the base. Right? Each face have 3 edges. 1, 2, 3. Right? Each face has 3 edges, and this is actually this is actually based on if you refer to the parallel pipe before, you're going to see that if you have 6 tetrahedron and you combine them, it will become parallel pipe. Right? Just imagine you have 6 objects of tetrahedron, combine it, and you will have the parallel pipe. So by using that logic, right, to obtain the volume of tetrahedron, we are just going to divide the volume of parallel pipe to 6. So you'll get the volume of tetrahedron. So that is how you calculate it. Now let's see how. Let's try to discuss exercise 3.12. Given the points this O, P, Q, and R, find the volume of parallel pipe with edges OP, OQ, and OR. So they already give us the 3 vector that we can use to calculate for the volume of parallel pipe. Just a little bit of revision. As you can see here, this is a given point, not in a vector. As a way to look at it, as you can see that the bracket here is a bracket of Cartesian coordinate. Alright, so we'll need to first look for the vector. However, as you can see, the origin point is 0, 0, 0. So it is easy actually to redefine all of this vector. So they will be the same value of each point here, with just a different bracket, just so that we know that this is a vector, not a point. Right? Now that we have this, we can proceed by using the formula of volume, which is this. Next is just to rearrange it. Right? where we have 1, 2, 3, and then 1, 1, 2. After that 2, 1, 1. Okay, let's calculate that. Alright, remember the way to calculate this is just the same as we calculate cofactor before. So we have 1 times 1 minus 2 negative 1. Right, so there you have it. The answer is 2, the volume for the parallel pipe. Next, from 1, find the volume of tetrahedron, and as we discussed before, the volume of tetrahedron is actually part of 6 times, right? 6 times the volume of parallel pipe, because tetrahedron is actually by itself 6 can be split into combined into 6 parts, right, to become parallel pipe, right? So to find the volume of tetrahedron, we just use the formula of the same formula, right? The same formula. But now we divide it by 6. Alright, or we can say 2 over 6. Right, simplify 1 over 3. That is the answer. Right, that is the volume of tetrahedron. Right, so that is for the application, right, in finding the volume of parallel pipe and tetrahedron. Thank you.